this video, we'll be looking at power series. When you are looking for the interval of convergence, a minus r to a plus r, where a is the center of the power series and r is the radius of convergence, the series always converges in one of three ways. So it could converge only at one point, x is equal to a, and diverge everywhere else, in which case the radius of convergence is 0. 2, or it could converge for all x, so the radius of convergence is infinity, and the interval of convergence is minus infinity to infinity. 3, or it could converge around the center x is equal to a with radius r. So from a minus r to a plus r, we'll see that it converges when the absolute value of x minus a is strictly less than r, and it diverges when the absolute value of x minus a is strictly greater than r. When you want to find the interval of convergence for your power series, you'll use ratio test to find the radius of convergence r. And sometimes root test could also be used. If you have some finite interval of convergence, you must test the endpoints of the interval separately to see whether it converges or diverges at the endpoints. So in this example, find the radius and interval of convergence for this power series. So here we'll take the limit as n becomes large of the absolute value of the n plus 1th term over the nth term, 2 times n plus 1 brackets plus 1 will be 2n plus 2 plus 1. So it'll be 2n plus 3. So we have the absolute value of x to the 2n plus 3 over 2n plus 3 factorial. And I won't rewrite the alternating part since we're taking the absolute value. This will be divided by the nth term, but instead I will multiply by its reciprocal. So after we can cancel x to the 2n plus 1 from the top and bottom, then x squared will be left. And the larger factorial 2n plus 3 factorial, we can rewrite as 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. That way we can cancel 2n plus 1 factorial. So the limit as n becomes large of x squared over 2n plus 3 times 2n plus 2. When n becomes large, the bottom is infinity, so it will go to 0, which is less than 1. So the interval of convergence for the power series is minus infinity to infinity, and the radius of convergence is infinity. Next, find the radius and interval of convergence of this power series. We'll use the ratio test. N plus 1 factorial, x to the n plus 1. So that's the n plus 1th term divided by the nth term, n factorial times x to the n. So we've rewritten n plus 1 factorial as n plus 1 times n factorial. So we can cancel n factorial in the top and bottom. X to the n plus 1, we can cancel from the top and bottom, and x is left. So we take the limit as n becomes large of n plus 1 times x, which is infinity, so it diverges for all x values, except x is equal to 0. So the power series converges at x is equal to 0 only, and the radius of convergence is 0. Find the radius and interval of convergence of this power series. So again, we'll use ratio test. So x to the n plus 1 over n plus 1 squared, and instead of dividing by the nth term, we'll multiply by its reciprocal. So if we cancel x to the n in the top and bottom, we'll just be left with x to the 1 on top, times n squared over n plus 1 all squared is n squared plus 2n plus 1. So here we get infinity over infinity. The top and bottom have the same degree, so the limit will just be the ratio of the coefficients. So the limit will just be absolute value of x, which only converges when it is strictly less than 1. Next, we'll check the endpoints. So when x is equal to 1, we can replace that in the original series. So here, it's a convergent p series with p is equal to 2. So then we can include the endpoint x is equal to 1. When x is equal to minus 1, we have the alternating version of that series. So when x is equal to minus 1, the series is absolutely convergent, so we can include both the endpoints. So since we included both the endpoints, the interval of convergence is minus 1 to 1, including minus 1 and 1. And the radius of convergence is always half that interval, r is equal to 1. Next, find the radius and interval of convergence for this power series. So the limit as n becomes large of the n plus 1th term times the reciprocal of the nth term. So here you can cancel x minus 5 to the n from the top and bottom. Then x minus 5 will be left on top. And we can cancel 4 to the n from the top and bottom, and then 4 will be left in the denominator. So we take the limit as n becomes large, we have infinity over infinity. Once again, they have the same degree in the top and bottom, it'll just be the ratio of their coefficients. So here the limit x minus 5 over 4 in absolute value must be strictly less than 1 to converge. So here we see that around the center 5, we have a radius of convergence of 4. If we let go of the absolute value, we have that x minus 5 is in between minus 4 and 4. We have x is in between 1 and 9. So since we have this finite interval of convergence, we'll check the endpoints to see if we will include them or not. So we'll check the endpoints. At x is equal to 1, if you plug it into the original function, we get this series. So if we simplify, The two alternating parts will cancel each other out, and 4 to the n and 4 to the n will cancel out. So we're just left with the series 1 over n, which we know is the divergent harmonic series. So we won't include the endpoint x is equal to 1. Next, when x is equal to 9, we have this series. 9 minus 5 is 4 to the n. So we can cancel 4 to the n in the top and bottom. So this was the alternating harmonic series, which we know is convergent by the alternating series test. So it passes the divergence test, and the next term is smaller than or equal to the previous. So since it's convergent at x is equal to 9, we will include that endpoint. So the interval of convergence is from 1 to 9. We checked the endpoints. It was divergent at x is equal to 1, so we don't include that endpoint. Here I wrote soft bracket. Some people might write backwards hard bracket. It's up to you. And at x is equal to 9, it was convergent, so I'm including that endpoint.